Okay. All right, so basically we're gonna start doing the homework. So I'm gonna start from week 7. I think that's one of the ones we need to address. So this would be week 7, and basically from here we'll just do the homeworks one by one. Hopefully this will help you guys do the homework, since I'm literally just giving you the answers. All right, so week 7. All right, so first problem. We have the set B is equal to -1, 3, 0, 0, 0, -1, 0, 3, and then 0, 0, 0, 2, like this, right? And by the way, if you guys have any questions, you can like stop me at any time you want. So is a basis for the space of upper triangular 2x2 matrices. So we just need to find the coordinates of M, which is this matrix here, -1, -5, 0, -2, with respect to B, the basis B, okay? So if you remember, actually, this was like this past class, right? So we talked about coordinates of spaces with respect to other vectors. So here, basically what we want to do is we want to find C1, C2, and C3 such that what? The matrix M, -1, 0, -5, -2 is equal to C1 times these matrices right here. Plus C2. And let me shrink this a bit. Plus C3 of 0, 0, 0, 2. Okay, so basically as soon as we find what these C1, C2, C3 is, these will become the coordinates of the of B with respect to B, okay? Okay, well, I mean, how can you solve this? Well, I mean, the easiest way is you can just maybe eyeball it. If you eyeball it, it might work, but I guess a more systematic way is just to set, so combining all matrices up here, we get -1, -5, 0, -2 is equal to, well, this is going to be minus C1, and then that's the first one. C2, so it's going to be 3C1 minus C2 for that one. So that's going to be 0 here, and then this is going to be 3C2 plus 2C3. Okay, which means in order for these two to be equal, we need to have that -C1 equals -1, 3C1 minus C2 equals -5, and also that 3c2 plus 2c3 is equal to minus 2. Okay? So from here, we can find our c's. So let's do that. So let me expand this a little bit. Well, from here we can find that c1 is going to equal to 1. And then from there, c2 is going to equal what? Well, if I do c, this will be minus, so it'll be 8. And c3 is going to equal to, so hold on, let me, if I plug it in, and then I'm going to get minus 13. So the matrix M with respect to the bases M or B is going to have coordinates 1, 8, minus 13. And this is the answer right here. Okay. Any questions? Nope. Okay. So next one. All right, so this is 2. So we're going to have to figure out which of the following are subspaces of P2. Okay, so basically here we have the first one, A. The set of all P of T is equal to, or such that the derivative at 8 is equal to P at 5, like this. Okay. Okay, well remember, all we have to do is check 3 things, right? We need to check that the 0 vector is in there, it's closed under addition, closed under scalar multiplication. So first thing, is 0 in here? Yes, of course, right? Since if P of T is equal to 0, then P prime of T is equal to 0. And so P prime at 8 is going to equal 0, and P at 5 is definitely going to equal to 0. So, which means that P prime of 8, oops, is going to equal to P of 5. So 0, so I'm going to call this S, by the way. So 0 is definitely an S. Okay, so it's for sure in there. So now it's 2. Let, I guess, P1 of T and P2 of T be in S. Then, okay, well, then what? Well, then observe the following. Okay, well, in order for it to be a member of S, it has to follow. It has to satisfy. So we okay. So I guess hold on. Let me see. So we need that P of 1 plus P. I guess okay, even better. I guess is P1 at T plus P of 2 of T in S. Well, observe the following. Well, P1 of T, or sorry, yeah. So let's take the derivative. So let's take the derivative of this and evaluate 8. So observe that P prime, P1 of T 8 plus P2 of 8, all at, so if you take this derivative, well, this is just going to be equal to what? well, it's going to equal to P prime 1 at 8 plus P2 prime at 8, right? The derivative you can distribute. But since P1 and P2 are members of S, they also have to satisfy that equality. So this has to equal P1 at 5 plus P2 at 5. So you see that the derivative at 8, so this is definitely, so this basically means that, so then I guess P1 plus P2 is definitely in S, okay? Okay, perfect. Oops. And then last but not least, scalar, the scalar multiplication. So let lambda be an R. And so, let lambda be an R and P of T be an S. Then, okay, well, lambda P at T, well, that's just going to be equal to lambda P, at, I guess, let's start at 5. P at 5. Well, since P is from S, this is also equal to P prime at 8, which is definitely just lambda P prime at 8. So lambda P is definitely in S as well. And so that one is a subspace for sure. Okay. Okay. So so that means A is also, so this one is so A is in the is a subspace. Okay, so I'm gonna do 2 more, and then basically, okay, so I'm gonna do maybe, so 2 more, and then I guess I'll leave the rest to you guys, but because I want to get through all the problems. So the second one, B, P at T such that P prime at T plus 2P of T plus 6 is equal to 0. And say this is S. Okay, first one. Is 0 in here? What do you guys think? Well, is P of T at 0, then P prime at T is also equal to 0. So plugging into that formula, so plugging it into here. No, hold on. So plugging into above gives us 0 plus 2 times 0 plus 6 is equal to 0, which means that you get 6 is equal to 0, which is not true. So that means 0 is not in S. So this is not a subspace. Okay. Okay, so that B is definitely not one. What about C? Well, C is this set right here, such that P at negative T is equal to negative P at T for all T. Okay, so again, 0 is an S. Is this true? Well, yeah, of course, right? So note that for P of T is equal to 0, P at negative T is just equal to 0, and negative P at T is also just equal to 0. So it definitely is an S. 2, is it closed under multiplication? Well, of course, right? So in other words, is if you get P1, P2, and S, is P1 plus P2 in S as well. Well, of course, right? So say you have P1 plus P2 at t. What this is going to equal, if you plug in negative here, what's this going to equal? Well, it's going to be P1 at negative t plus P2 at negative t, which is, well, since they come from S, they also have to satisfy P1 at t minus P2 at t. If you factor this out, you get P1 at t plus P2 at t, which is just going to be negative P1 plus P2 at t. So P1 plus P2 is definitely an S as well. Okay. And then let's see. Then 3. Well, lambda be in R and say P is in S, then lambda P at negative t is going to equal to lambda of P at negative t, which is going to be negative lambda P of t, which is definitely just negative lambda P at t. So lambda P is an S as well. So it's a subspace. Okay. Okay, so I guess I can just try to do the rest of them here. It won't take too much longer. Since there's D, E, and F, right? So this one's D. So S is equal to the set P of t is equal to such that P prime at t is constant. Well, again, is 0 in here? Yes, because if P of t is equal to 0, then P prime of t is also equal to 0, which is a constant. So the derivative is a constant, so it's in there. 2. Okay, let P1 and P2 be in S. Then taking the derivative of P1 plus P2 of t, taking this derivative, is just going to be P1 at t, the derivative of this, plus P2 at t, the derivative of this. But since P1 and P2 come from S, they're also constant. So these things right here are also constant. So that means that, what does that mean? Well, it means that it's also an S, right? So this is, so P1 plus P2 is an S. Okay, let's do it. So it's a subspace. Let's do E. So let's set S equals the set of all P of t such that the integral from 0 to 3 of P of t is dt is equal to 0. Well, clearly 0 is an S, right? The integral of 0 is always 0. So this is immediately true. P1 plus P2 in S? Well, yes. Because if you integrate P1 at t plus P2 at t from 0 to 3 dt, you're going to just distribute the integral for each one like this. And since each one comes from S, this has to be equal to 0 plus 0, which is equal to 0. So P1 comma P2 is in S. And then 3, same thing, same argument. So all of these are, and you say this is a subspace. Last but not least, F. Let S equal the set of all P of t is equal to, or sorry, such that P of 2 equals 5 is true, right? So again, I mean, is this a subspace? Well, for P of t is equal to 0, we have that P at 2 is equal to 0, which is not 5. So 0 is not an S. So it's not a subspace. Okay, and you're finished with that one, basically. Okay, so problem 3 is basically similar to this. You just do the exact same thing. So I'll leave that up to you guys to do. You basically do the same arguments. You just check if 0's in there. You check if the addition is closed. You check if if the scalar multiplication is closed. So for problem 3 in week 7, for example, A says the vector space of all n by n matrices, and S is the subset of all upper triangular matrices, right? So we need to check if S is a subspace. So I mean, 0 is definitely there because it's a triangular matrix. The addition of two triangular matrices are triangular again. Scalar multiplication on a triangular matrix is again triangular, so it is a subspace. So that's one. But anyway, so yeah, you just do that, and that basically give you the answer. So basically the same step that we did here. All right, so let's do number 4 now. So we have that a square matrix is nilpotent if a to the n is equal to 0 for some n in n, right? So it just means that if you take the matrix, raise it to enough powers, you get 0, right? Okay, so first question. So it says let V be the vector space of all 2 by 2 nilpotent matrices, or I guess matrices, right? With real entries, and let H, a subset of V, be the set of all 2 by 2 matrices, or nilpotent matrices. And the question is again, is H a subspace of V? Well, I guess the very first question is, does H contain the 0 vector? Well, I mean, yeah, right, because 0 to the first power is 0, so it's always in there. So 0, so H contains the 0 vector. Okay. Is H closed under addition? If it is closed, if it is interclosed, right? So I guess let me put 2. If it is not, enter 2 matrices whose sum is not in H. Using comma separate. Okay. Okay, so basically we just need, so we just need to show that is it closed under addition, right? So I mean, you can think about some matrices that don't satisfy this, right? Well, the most easiest thing to do is just basically do this. So let I don't know, for example, what is probably the best way to do this? Sorry, hold on, let me think about this. Yeah, right, okay. So let, I don't know, A and B be in H, right? Then what is, I guess, maybe say oh yeah, let's see. So okay, so now I guess what is then a to the n is equal to 0, and ma or b to the m is 0, right? So I mean, we have these conditions for both of them, right? So we just need to show that it's closed. So take a plus b. Now, if n and m are, I guess, the numbers, just pick the one that's bigger and raise it to that. Let's just say that's n, right? Well, what is this going to be? Well, let's just test out a few cases. We don't have to prove it at all. We can prove it using induction, but let's just use, let's just say for argument's sake, this was, I don't know, let's say both of them are like squared, okay? Let's just say, okay, so now square this. Okay, so, well, this is going to be a plus b. A plus b is going to equal to what? Well, it's going to equal to a squared plus ab plus ba plus b squared, right? Well, what is this going to equal to? Well, oops, sorry. Well, this is just going to equal, so since this part is squared, this would give me 0. Since this part is also squared, this will also give me 0. But notice that here, oops, you just get AB plus BA, which basically tells me that this could be not 0, right? So basically it tells me that this is not closed, right? So definitely this is definitely not closed. This already tells me that it isn't closed. I just took an example and it showed that it's not closed. So for sure this is not closed. Oops, sorry. So not closed for sure. Okay. Okay, well, now we have to find two matrices that, I guess you could say this is not equal to 0 in general, right? Well, I guess two such matrices. Well, I mean, you can probably just think of it, right? So you can maybe do 0, 1, 0, 0, and then, I don't know, do 0, 0, 1, 0. Okay, so obviously this one squared is equal to the 0 matrix. This one, I guess, squared, so if you square it, it also gives me the 0 matrix, right? And if you do 0, 1, 1, 0, 0, and then add it, this will give me 0, 1, 1, 0. Now square this, you get 0, 1, 1, 0. And if you square it, you get 1, which is, I mean, you already know that it's not 0, right? 0, 0, 1. So this gave me the identity. So this is not 0. So these are two matrices. So you can just pick these to be my two matrices that give it to you. So okay, so obviously it's not closed. So no problems there. The third part is scalar multiplication closed. Well, let lambda be an R and I don't know, say A be an H. So a to the n is equal to 0 for some n, right? Okay, well then do lambda to the a to the n, which is just going to be lambda to the n to the, like this. but that's going to be 0, so it is closed. And then the fourth part, well, and since you weren't able to, since the first one wasn't closed, the addition, it's not a subspace. Okay. All right. So, okay, so let's go to, I guess, other problems now. So I'm gonna skip problem 5 because it's the exact same thing. Problem 6 as well. Let's do problem 8 now. Okay. So we'll do problem 8, and we'll basically go back to problem 7 because that basically connects with problem 7. Okay, so let's do problem 8. So find a basis, let's say P of X, Q of X, of the vector space, I don't know, that's in P3, such that F prime at 7 is equal to F at 1, where P here is the vector space of polynomials in X with degree less than 3. Okay. Okay. So this one, you basically have to okay, so just look at this part right here. Let's look at this guy. What is something that in there that what is something that looks like in here? Well, I don't know, say f of x equal ax squared plus bx plus c, which, right? So we need to see exactly when. So now the question is, when is f of x in, I guess let me call this set S, right? So when is f of x in here? Well, it's in there exactly when its derivative at 7 is equal to it evaluated at 1, right? So take the derivative. So take f prime at x, which would give me 2ax plus b, and then obviously, right? So we have this, then evaluating at f prime at 7 is going to give me 14a plus b, and then evaluating f at 7 is going to give me, well, it's going to be 7 times 7, so it's 49. Oh, sorry, f of 1, right? It's going to be f at 1. What is just going to give me a plus b plus c, okay? And we know in order for that to be in the subspace, it has to these two have to equal. For f to be in S, we need that 14a plus b is equal to a plus b plus c. Okay? Okay, well then, I mean, you know how to solve a system now, right? So solve this, right? So, I mean, best thing you can do here, so I'm just here, let me take this over here. Solving, I don't know, let's solve for, okay, well, solving, you know that this guy's gonna cancel with that guy. And basically you get 14a is equal to a plus c, which means that c is going to equal to 13a, right? So plugging conditions back into, say, f of x equals ax squared plus bx plus b plus c. We're going to plug this in now, okay? So we plug this in, we get f of x is going to have to equal ax squared plus bx, and c was 13a, so plus 13a. Now what I'm going to do is I'm going to collect the like terms like this in a. And now factor on a, you get a times x squared plus 13 plus b times x. These things are vectors, right? These are in my vector space S, or sorry, I guess these are in P3, right? Which means, and look, this is an A and B are constants, right? So that means that anything that's a linear combination of both x squared plus 13 and x are a basis for that. So I guess you can say, so then b is equal to the space x squared plus 13, and x is a basis. Okay, so that's how you do this one. Let's see. Okay, so let's see. Why not? Okay, so let's go back to problem 7. So let P2 be the vector space, basically be the vector space of all things that look like this. And H be the space spanned by 2x squared plus 10x minus 7 and x cubed plus 4x minus 3, and also, well, then there's a lot of vectors. Okay. 5 minus 2x squared plus 6x, like this. All right. So okay, so I guess here then becomes, what is the dimension of H, right? Well, oops, sorry. So basically, what is a basis again, right? So a basis is exactly when, let's see, is the number, sorry, what is the dimension? So the dimension is basically the number of basis elements in my vector space, right? Here we're taking a span of 3 things. However, we're not sure if this forms a basis for it. So remember what it means. What does it mean to be a basis? First, it has to span the entire thing, which by definition this will span H. However, it also has to be linearly independent, right? Meaning none of these can be constant multiples of any other thing. So I guess part A, what is the dimension of H? So solution, observe that, well, let's see, 2x squared plus 10x minus 7 and x squared plus 4x minus 3. Well, can I get any of these two? Can I go between any of these two by multiplying by some constant? Sorry, hold on. Well, let's see. Did I copy that right? I think I did. And then do 2, that would be 8 minus 5. So hold on, give me a quick second. So let's see. So we have 2x squared plus 10x minus 7, and 5 minus 2x squared minus 6x. Can I get any one of these as a constant multiple of the other? Oh, well, hold on. Yeah, that's right. That's right. So I guess if I do this, that'll be 3. That would be so hold on, give me a second. So observe the following then. Do C1 times 2x squared plus 10x plus C2 x squared plus 4. Oh yeah, that's right. We can also check if they're linearly independent if we have the following. Sorry, that was bad. So we have to just check that C1 times 2x squared plus C2 x squared plus 4x minus 3 plus C 3 5 minus 2 2x squared plus 6x. Okay, so let's see. Let me shrink this a little bit. Is equal to 0 now. Okay. So combine everything. So we're gonna get, I don't know. So if you combine everything, you're gonna get there should be just a minus there. Okay, so we'll get C2 C1 plus C2 minus 2C3, all of this x squared plus 10C1 plus 4C2 minus 6C3 x plus, and then finally minus 7C1 plus minus 3C2 where is it? C2. Oh, sorry, C2, and then plus 5C3 is equal to, yeah, and this all is equal. So from here you just get the equations 2C1 plus C2 minus 2C3 minus 7C1 minus 3C2 plus 5C3. All this equals 0. That equals 0. 10C1 plus 4C2 minus 6C3 is equal to 0. So if you were to RREF this, what you'll find is that you'll get a something that won't give you all of these C. So remember, so what would it mean for this to be linear independent? It means all C1, C2, C3 is 0, right? So what you're gonna find is that none of these will be just identically 0. And if you repeat this with 2 of them, if you just do 2 of them, like for example, if I were to just RAF the stuff without without one more, you'll find that would actually give you C1, C2 gives you 0. So that means that there's two basis elements in H. So the dimension of H has to be equal to 2. Okay. So by the way, since the dimension is 2 and you have 3 things in your span, of course it's not going to be a basis. So So not a basis. So part B just asks you, is it a basis for H? It's obviously not, so not a basis for P2. Well, even better, it's just not, just straight up not a basis because you can't get this as a consistent basis. So so by the way, we said that only 2 of these will be it, so you can just choose this one, and I guess this one would be the other one. So oops. So see, the only basis that we have here is for H is B is going to equal to 2x squared plus 10x minus 7 and x squared plus 4x plus 3, or minus 3, sorry. Okay, so the dimension is 2, not a basis, because if it doesn't, because it's only going to span H, so it's definitely not going to span P2. If it did, then the subspace was just being the entire thing. Okay, so next one, I guess. Okay, so 9. Let's do 9 really quick. So we'll basically do 9, sum of 10, and then sum of 11 as well. Okay, so we have a square matrix. Is half magic. If the sum of the numbers of each row is the same. So find a basis for basis B, I guess, for the vector space of 2 by 2 half magic matrices. Matrices. Okay, so solution. So let A, B, C, and D be a half magic matrix, right? Well, not just basically. So basically, what we're going to do is we're going to try to find conditions on A, B, C, and D. So it says that since the rows and the columns have to be the same, if you add them up, that means that A plus B has to equal A plus C. And also, I guess, what is it? A plus B has to equal A, and then we also have that C plus D is equal to B plus D. C. Yeah. So from here, we can get that B has to equal to C. From these two, right? But what about the other one? So what about, so this was one pair. What about A plus C? That has to equal to, sorry. So the rows, okay, so let's see. What was the other one? So that gives me B equals C. The other one's gonna give me A, C, B, D. So let's see, B, C equals. Yeah, well, I mean, all the other ones, A plus B equals C plus D. Yeah, so none of the other ones give me much, right? I guess what it does give me is, well, since B and C equal, this one's gonna give me A equals D, right? So basically from here, so I don't know. So basically how I got this one first is I equated this one with this one like this. How I got, I guess, this one right here, I did that one and this one. So A plus B equals C plus D, right? Okay, so we have conditions now. So that's all. That's the only conditions we can find on our matrices. I mean, once you have A equals, yeah, I'll send these out as well. So every matrix of the form. So I mean, since A equals D, we're just gonna say A, and since B equals C, so it'll be B, B, D, D, or A, like this, right? Okay, let's write it like this: A, 0, 0, plus 0, B, B, 0, right? So this is just going to be A times 1, 0, 0, 1, plus B, 0, 1, 1, 0. These guys right here are in are in my space. So that means that these have to be the basis elements. So this is a linear combination of the vectors. In this case, are the half magic matrices. So you can see that it's that. So these are definitely in my space of half magic matrices. So the basis would become this: 1, 0, 0, 1, 0, 1, 1, 0. Okay, so this is the basis right here. Okay, let's go to the next one. Any questions? No. Okay. 10. So we're gonna find the dimensions of each of these vector spaces, right? So A. So the vector space of 6 by 6 matrices with trace equals to 0. So so for this one, we can do this. So just remember the trace is the sum of the diagonals, right? So if you sum up the diagonals, they should be equal to 0. In other words, if you have, say, A11, A22, all the way to A66, and who cares what all this other stuff is? So if we have this, right, then in order to be what we just said, then we need that A11 plus all the way to A66 has to be 0. Or in other words, A11, it has to equal minus A22 minus A33 minus all the way to A66, right? So that means that you can write the above. So the above becomes yeah. So hold on, give me a second. So the above becomes basically this: minus A22 minus A33 all the way to minus A66. And then you have A22 here all the way to A66 here, right? And again, who cares what this all is? All right, so from here, what can we do? Well, we can split this up into its components. Oh, okay, I see. So I guess this is not enough yet, because I mean, yeah, because I can't. Oh no, it is enough. However, it's gonna be quite troublesome. So So let's do this. So we can write this as the following. So this is going to equal to, okay. So I want to write this in terms of yeah. Yeah, because so notice here, so you get negative 822 here, right? Um, uh, oh goodness, yeah, that's right. You're gonna have to just split this up completely. Oh, yeah, I see. Okay. Okay, I see. So you're just gonna have to because remember what are we trying to do here? If we can find a basis for for this stuff right here, that would be the dimension. So basically I want to write it in terms like V1, C1 plus C2, V2, and so on and so forth. So I need to see how many of these V's I get, right? In this case, they're matrices. But the problem here is that in order for me to write this as a linear combination of other matrices that have trace 0, I have to basically split them up. So that'd be oh yeah, okay, so I'm gonna have to do everything on the right hand side over here, and then I'm gonna have to do everything on the bottom, which then becomes that's a okay. So basically, okay, so there's 6 elements down there. The trace of those things would be 0. But what about, okay, so once I write it all like that, what can I do? Well, then I have to like write it in terms, okay, so basically what I'm going to do is I'm going to have to write everything in terms like A21. Oh goodness, yeah, this one is a little bit harder to see, but basically basically what you have to do now is for each element or each entry in your matrix, you're gonna have to like write it as a multiple of, yeah, so you would have to do like basically A21 times like 0 0 all the way, and then like one entry here, and everything else is 0. And you do that for each entry. But the only entry you wouldn't do it for is the first one. So if you don't do it for the first one, but hold on. So okay, so you're gonna get at least 32, at least a dimension of 32 here. So rather 30. You're gonna have at least dimension 30 because you're gonna have to do this. Okay. So once you do that, you can write everything else in terms. So yeah, so all of those will be fine. What about the diagonal? The diagonal is the one that troubles me. There you can just write it as 1 times this. So it should be 35, I believe. It should be 35. So yeah, so 30, 30, 30. And then the last one is just going to give me yeah. So I believe the answer is 35. If someone can check it or it has checked it, I think that the answer should be 35 because you have to split it up among 35 different things. And so you only have one left. and due to this part right here, it's just gonna be 1 left over, so you don't need to worry about that one. Yeah, okay, perfect. Yeah, so it's 35, yeah. Okay, well, well, that one was a pretty, okay, well, yeah, because you have to, like, just forget about this one. I just gave you the answer, it's 35, so you don't have to worry about it, so answer here. Yeah, and, okay, so part B. The vector space P7 with degree less than 7. Well, the basis there is just going to be, I mean, I can immediately say this would be a basis, right? Less than that, so it's going to be 1, 2, 3, 4, 5, 6, 7. So it's going to be dimension of P7 of X is 7. Okay, so that's B. What about C? Vector space of R5. The dimension of R5, you can clearly see that's 5, so you don't have to worry about that. D, 2 by 3 matrices. The dimension of, okay, 2 by 3 matrices. Okay, so let's. Okay, so we need to find. So okay, so it was a 3 by 3. You would just have 1, 1, 2. Okay, so in order to build a 2 by 3, so you have A, B, C, D, E, F. Well, I can build it with A times 1, 0, 0, 0, 0, 0 plus B times 0, 1, 0, 0, 0, 0 plus C 0, 0, 1, 0, 0, 0 plus D times 0, 0, 0, 1, 0, 0 plus E 0, 0, 0, 0, 1, 0 and then plus F, which is 0, 0, 0, 0, 0, 1. So how many bases? So there's 1, 2, 3, 4, 5, and 6. So this is going to be dimension 6. So yeah, so basically what I was trying to do with the first problem was I was trying to write this ugly thing like this. And it turned out you had to do it with 35 different ones. So that's why the dimension would have to be 35. Okay. Perfect. All right, so what about E? The vector space of all diagonal 6 by 6 matrices. So E, 6 by 6 diagonal matrices. Okay, well, again, for this one, take a diagonal A11 all the way to A66. This doesn't matter, so you can write this as A11, 1, 0, 0, basically 0, 0. So if you do this, you're going to have one for each one, right? So basically A22, 0, 1, and then everything else is 0. All this is 0. And you continue this until you get A66. So you're going to 0, whatever, and then 1 here, 0, 0. So there's going to be a total of 6. So the dimension is equal to 6. What about F? Well, the vector space of 4 by 4 lower triangular matrices. Well, what about those? Well, these will just be like A11 all the way to A66 or 44. So A22, A33, A44, and then there's stuff down here, right? Well, I'm gonna have one for each stuff in the diagonal, so it's gonna be at least 4 there, what about the other stuff? Well, there's going to be 1. Well, I guess you can just say what is the area of this triangle, I guess. So there's going to be 4 down here. There's going to be 4 up here. 1/2, 4 times 4. So 4, 4, 16. Oh, I guess we have to also get the perimeter. Well, okay, so there's going to be what? So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10 right there. Okay, so there's going to be its dimension is going to be 10 because you're going to have to split that up 10 to 10. Okay, that pretty much solves that one. Okay, let's do the next one. I guess the last one. So 11, like u equal the span of 0, -1, 2, 4, -5, 4, and then v or w, sorry, is equal to the span of -3, 4, -3, -2, 4, -4. Okay. And V is the vector space of all 1/3 matrices. So find an X in V such that V is in U intersect W, which is equal to the span of X. Oh, sorry, and it's X. Okay. All right, so in order to find a basis for this, we need to find all linear combinations. So first of all, what does it mean to be in U? It means it's a linear combination of those 2 elements there. And to be in W, it means it has to be a linear combination of those 2 elements in there, right? So we need something that is a linear combination of both elements. Okay, I see. Right, so in order to be a linear combination of both things, so we need X, which will be, I don't know, say A, B, and C, such that X is equal to the, I guess, linear combination of all those. Right? And also, X has to be a linear combination of, say, B1, right? Okay. So what should it be? Well then. Okay, so we're gonna get. Okay, so we right now we have 4 unknowns, and since we have 4 unknowns, how many equations can we get? So we can get 1, 2, 3. We can definitely get 3 equations out of this. Okay, so let's do that. So we have that, well, the vector 0 minus C1, 2C1. Oh, I guess I'd rather, so I guess if we combine everything in the first one, you're going to get 0 minus C1 minus 5C2 and then 2C1. Oh yeah, this one would have to be 4C2. So here. All right, so it's going to be then 2C1 plus 4C2 is going to be equal to minus 3B1 minus 2B2. So let's see, where's the other one? Minus 2B2, and we have 4B1 plus 4B2, and then minus 3B1 minus 4B2. So we're going to get the equations 4C2 is equal to minus 3B1 minus 2B2. 4B1 plus 4B2 is going to equal to minus C1 minus 5C2. And then 2C1 plus 4C2 is going to equal to minus 3B1 minus 4B2. Okay. So we have 1, 2, 3, 4. So we have 4 unknowns and 3 equations. Perfect. So basically at this point, all we have to do is solve for this. So I mean, we can just set up an augmented matrix like this. So I don't know, say C1. So the first one will be 0, 4, minus 3, minus 2, 0, minus 1, minus 5, 4, 4, 0, 2, 4, minus 3. Oh, shoot, sorry. There should be that. There should be that. For 4, see 1, 2, 3, and then 4, 0. So if you RREF this, you should get some conditions. So I guess I'll just do it here. This should be the last one though. Like after this, we're done. RREF calculator. So let me just do this. 3 by 4, 3 by 5. 0, 4, 3, 2, 0, 1, 5, 4, 0, 2, 4, 3, 4, 0. All right, so let's see what we get. All right, so we get well, we get 1, 0, 0, 1, 0, 1, 0, minus 1, 0, 0, 1, 2, 0, which means I get that C1 has to equal to minus B2. C2 has to equal to, minus, or B2. And that B1 has to equal to minus 2 B2. So as long as it can satisfy this condition, it should be fine. So I don't know. So that means that we have that C1, C2, C3. So let's take this over here. Copy. So that means that this here is going to give us C1, C2, B1, B2 is going to give me minus B2, B2, minus 2B2, and B2. So, oh yeah, and B2 is free, I guess. So it's any linear combination of B2 minus 1, 1, minus 2, 1. So okay, so I guess once you do this, you can just pick B1 to be 1. So once you do that, you just plug this back into, well, you can just plug this into any of the two. So if you do that, then I guess you get minus, so C1 has to be minus 1, 1. So then plus, plus, plus. So I think x, so if you do this, so x has to be equal to minus 2, 2, and minus 1. So I mean, after this, you just have to like plug the stuff back in. So I don't know, pick B2 equal 1. Plug in your stuff. That should give you a thing that's in there. So you can just pick something B1, and then this would be the matrix. That's what, yeah. So just tell me, is this right, by the way? I guess whoever. Well, I mean, I guess I'm pretty sure it's. Hold on. Oh, sorry. Give me a second. Oops. Wait. No, that's right. This is fine. Yeah. Well, yeah. You can have different numbers because it's any. I mean, I picked this to be 1. So if I picked it to be 2, you can have a different set of numbers. I don't know what you did at the end. So basically at this point, I found conditions to my, okay, so basically what should happen is that if I pick B2 equals B1, then I get that. So if I pick that, then I get that C1 has to be -1, C2 has to be 1, C3 has to be -2, and, oh, sorry. B2 has to be this, or B, and then B, oops. Right, so that means that if I take the linear combination over here, so that, I don't know, say this one. With that C1 and C2. So plug it in here. So let C1 equal whatever -1. And C2 equal, I don't know, 1. Oh, I guess so X is gonna equal to -1, 0, -1, 2, plus 1 times this. So you get 0, 1, minus 2, plus, which gives me, well, it should be 4, minus 4, and yeah, exactly. Then 2, which I guess, I mean, it's a linear combination. I mean, it's just a constant multiple of what I just wrote up there anyway. So I guess this is also equal to 2 times, or -2 times, -2, 2, and -1. So this is the first thing I wrote, right? So you can just, I mean, it doesn't matter. You just plug in and you just find it. So basically what I did is I found a x that's in both, right? And since this is in both, but yeah, it doesn't matter. It's whatever you pick your B1 to be in the first place, that's what would give it to you. But I guess you can just choose that one. That'll be fine as well. Any multiple of this would be fine. So if you got different numbers, as long as it's a multiple of this, it's fine as well. Okay. Any questions? No problem. Well, we'll do week 8, I guess, tomorrow, and I'll upload this recording when I can. But yeah, we'll go through week 7, 8, 9, 10, and then I think there's 12. And basically we'll go up after this because I think everybody was like struggling with, I guess, these later homeworks. But at least you have some of them and you have some idea of how we did it. And okay, so no more questions? No? Okay, well then I will see you guys tomorrow. It'll probably be at 3 again, or 3, or I'll email you guys or remind you what time. Or let's just say 3 for right now. Okay. All right. All right, bye.